I hope you have had a nice evening. So we continue with the program. So our first speaker this morning is Robert Nowak, and he will be talking about learning low-dimensional metrics.
Okay. Thank you, Homer. Thank you to the organizers for putting together this workshop, and thanks for giving me the chance to participate. So let me explain this picture that I'm showing you here. This started with a conversation I had with a cognitive scientist colleague, Tim Rogers, and he was doing experiments in his lab where he would ask people to look at three faces like these and answer the question, is the emotion displayed in face I more like the emotion in face J or K? And if you ask people many questions of this sort and apply what's commonly referred to as non-metric multidimensional scaling, you can get a representation like the one I'm showing you here, a sort of metric representation of those comparative judgments. And so the idea is that we're hypothesizing that the comparative judgments are consistent with some latent metric representation. And so each face now is associated with a point Z in R2 in this example. And so psychologists, cognitive scientists like to do this sort of thing so that they can understand maybe how people are, what features might be driving their decisions and judgments about things like this. And a question that naturally occurred to me when he showed me this, because he asked, well, first I should say Tim asked a question. He said, how many comparative judgments do we need to learn an embedding like this? And I said, well, that's a good question. I'm not sure. And then I said, I was wondering, is it even clear that if I collected an enormous number of such judgments that we could recover a kind of consistent embedding or representation? So you could imagine sort of the inverse problem. Suppose I start off with the embedding, then I use this metric representation to generate comparative judgments according to distances. Is it even true that I can go backwards and invert that process and recover the generative model, if indeed there was a generative model? Okay, so those are the questions that sort of came up in my mind, and as I started to look at the literature, which goes back over 50 years, I realized that there were a lot of open questions of this sort that really no one had addressed, and so we started to look at it more carefully. So the basic problem that I just showed you is what is called non-metric multidimensional scaling or ordinal embedding. The idea is you're given a bunch of ordinal information in the form of these distance comparisons between points, and then you're trying to learn a metric representation that agrees with those comparative, those distance comparisons or ordinal information. Another kind of extension, if you will, of this is what's commonly referred to as metric learning in the machine learning literature. And the idea here is exactly the same, except in addition to the ordinal information, you also have some raw feature information. So what I'm imagining here is you start off with some original, maybe very high dimensional representation. You have that representation plus some distance comparisons, and now you want to find a lower dimensional metric representation based on that original one, sort of a mapping of this form. So I want to find this kernel matrix, if you will, that maps the original points into a lower dimensional representation that's consistent with the ordinal information. That's called metric learning. Okay. The case that I just described before, ordinal embedding, is a special case where the original representation is just the kind of trivial one where each point is represented by one coordinate axis. I'll come back to that in a second, but they're essentially that problem's a special case of metric learning. Okay, so, there we go. So where do people use this? Well, one way machine learning people use metric learning is they try to learn this nicer low-dimensional representation, and then they could run k-nearest neighbors or do some clustering or whatever downstream machine learning they'd like to do. The other main application is understanding or visualizing human perceptions, preferences, reasoning, and so forth. That's sort of where my colleague Tim got me started on this. There are a bunch of applications. If you look at metric learning or in Google Scholar, you'll find that people use it for computer vision, image retrieval, bioinformatics, and I'm going to focus on this cognitive science type of application. Here are two of the famous papers in the machine learning literature that have generated a lot of citations. So this is a popular topic and has seen a lot of activity in recent years. Let me just, before I get into some more of the mathematics, let me just give you another motivating example. This is an educational science with my colleague Martina Rao. She develops tutoring systems for chemistry, and her setup is very similar. She would have a target molecule, two choice molecules, and she'd ask beginning students which of the two choice molecules is more similar chemically to the target. And by asking people many questions of this sort, we can see how their judgments align with known chemical groups and so forth. So this is the embedding that was generated from comparative judgments of that type. Some of the things you'd like to do is, here's kind of a representation. Maybe the features that beginning students attend to are simply counting up the number of different types of atoms. So how many oxygen, how many hydrogen, how many carbon. And so if we did that, maybe this is the representation of those points in space. And what we might want to do is, for example, find a low-dimensional representation of such data. So here I'm trying to show how we would maybe find a mapping from the three-dimensional space into a lower two-dimensional space. And we could do that by using a low-rank kernel matrix K. So this is a rank 2 matrix right here, and that gives us that representation. And this would be, for example, convenient if Martina wanted to visualize in 2 dimensions what's going on. What are the 2 most important dimensions that students are attending to? The other thing you might try to do is to actually find a sparse metric. And so what would a sparse metric do? It would say, well, maybe students aren't even really paying attention to the number of oxygen. They simply look at how many hydrogen and how many carbon appear in the molecules, and that's the basis for their judgments. And that kind of perceptual process could be represented by a sparse and low-dimensional metric like this one here. So here we're just showing that we don't pay attention to that third dimension, which is oxygen. Okay? So that's sparse and low-dimensional metrics. That's kind of the thing that we're trying to learn from these comparative distance measurements. All right, so as I said, ordinal embedding is the first problem I talked about, where we don't have any original feature representation. We just have the distance comparisons. You could imagine that's a special case of metric learning where I just take the original raw representation, if you will, just to be the canonical unit vector. So if I have n examples, n faces, I would just have canonical unit vectors in Rn. That would be my original representation. Then we want to find a low-dimensional representation of those points that agrees with the distance information. Okay, so here is just some of the classic literature. As I said, this is an old problem. Started back in the 60s by Shepard and Kruskal. Those were the 2 main guys who were looking at this, and they were primarily motivated by this kind of psychometrics type of problem. More recently, in machine learning, there's been a lot of work. And really, the classic methods basically just tackle the problem straight on. These are non-convex, messy problems in general, so they just came up with greedy or whatever strategies to try to fit embeddings to the ordinal information. And then what happened in the machine learning community over the past few years is they reformulated these non-convex optimizations. They came up with convex relaxations, and they mainly focused on the kind of optimization part of the story, and not so much on talking about, well, how many comparative judgments do I need to collect in order to get a good estimate of that embedding and so forth. So they didn't focus on those issues, and that's sort of where our work comes in. So the 2 problems that we tackled that were more or less open previously is, first of all, just identifiability. If I give you a bunch of these ordinal constraints, can you even hope to recover the metric? Is it even identifiable? It turns out that that's not very obvious, but it is in fact possible. I'll explain how as we go. And then the second question is the one that Tim originally put to me. How many questions do I need to ask people in order to learn one of these metrics? Sample complexity. All right, so the way we'll think about it then is as a generative model. So I have a metric representation which generates ordinal information, possibly with some noise. In other words, maybe some of those distance comparisons are flipped at random. And then what we'd like to do is, can we go back? Does an inverse exist? And this is the problem that really hasn't been answered prior to our work, and that's what I'll describe for you today. So here's the setup. I'm going to focus first of all in the first talk just to give you the high-level intuition of things on this ordinal embedding non-metric scaling problem. And then I'll go more into some of the details of how we get these results in the general metric learning case. But I think it's easier to understand just by thinking about ordinal embedding first. So we have a latent embedding, Z. These are the points, those faces in that picture of all the emotions. These are the locations where those faces should be. That's our latent embedding that we're trying to learn. We have a Euclidean distance matrix. And I can write that distance matrix as with this expression there. So those EIs are just the canonical unit vectors again, and K is the Gram matrix Z transpose Z. And we're going to collect comparisons. I'll call these triplets, and they will be answers to questions like, are I and J closer together than I and K? And those might be noisy, as I said. So what do I mean by noisy? I mean a picture like this. Maybe we'll imagine that this difference of distances governs the responses. If I is much further from K than J, then we're somewhere over here, and the person will probably respond yes. I is further from J than K, and so with high probability that would be 1. On the other hand, if this is very negative, then they'll say no, but there's some confusion if J and K are almost equally close to I. And so we might assume a logistic model like this for those responses. Okay, so the responses are possibly stochastic in this way, and we're going to collect many of these from maybe a crowd of people, and we're going to try to recover D, the distance matrix, and of course if we find D, we can just factorize it to get the latent embedding Z. Okay, is that clear? All right, so what can we, this is an example I'll use in a couple of places. Here are 5 points. Here's the distance matrix between those points. So those are the squared Euclidean distances. And just to bear in mind, all we're really trying to do is find this representation, this embedding up to rigid transformation. So we could translate it, we could rotate it, we could reflect it. That won't change the distances. So we can't learn those things. We can only learn the relative distances. And so for the most part, we'll just assume that the embedding is centered at the origin, and we're not going to, of course, we won't be able to recover rotations and reflections. Okay? So can we recover the distance matrix from differences of distances? So that's sort of the key question at some level in terms of identifiability. Remember, our model is that essentially we're measuring differences of distances, perhaps through this logistic function. So we're getting 1-bit measurements, but they're probably distributed according to this difference of distances. So in principle, if I collected enough of these 1-bit responses, I could average them in some way and recover the difference of distances. And so the question is, can I, from differences of distances, recover the distance matrix? Seems like a simple question. And I just want to introduce a little notation here. We can think of our measurements as governed by this inner product, where I'm just taking the trace of a matrix M with the Gram matrix Z transpose Z. That gives me the differences of distances. And that matrix M, our measurement matrix, if you will, is all zeros except in the IJK submatrix where it has this particular pattern. And that just picks off all the different inner products that you need in order to form that difference of distances. Okay, so what's the problem with difference measurements? Well, if you just think about, say, the simplex, here I have 2 triangles, and these are the 2 distance matrices, and of course the differences of the distances are all 0 because the points are equispaced from each other. And so we can't recover this structure. This is a dilation, if you will. It's not a rotation, not a reflection, not a translation, This is something we wouldn't want to be fooled by. We'd like to be able to distinguish between these two triangles, but we can't, at least in this picture, from differences of distances. And so when I was talking about a kind of preliminary version of some of this stuff at Oberwolfach about a year ago, Richard really kind of blew up. He got very angry and he went on a Twitter storm, and this was his tweet. He said, "How bad can these measurements be? Blind to average distance, bad or sick measurements." And I felt really bad when I saw that tweet come out. And you know how nasty Richard can be. So I thought, well, okay, I have to fix this. I have to fix this. And so, just kidding. Richard's a sweet guy. Okay. So it turns out it's not a problem as long as you have enough points. So you can have an orthogonal decomposition of distance matrices of this form. The problem is we can't measure the average distance between points because that average distance will be wiped out by the differencing operator. So J is just this matrix of all ones, and mu sub D is this average non-zero distance between points. And so we can write D as a matrix C plus the average distance between points times this J matrix. C is what I'll call the center distance matrix. This is the part that we can measure from differences. And then the second part here is the part that's unobservable, the part that's wiped out by our measurement operator. Okay? And so really the question of identifiability boils down then to, if I just measure C, can I get D back? And that turns out to be possible. Let me again go back to this little example. There are the 5 points. There's the distance matrix. This is the center distance matrix. Oops. This is the center distance matrix. And this is then this orthogonal decomposition into these two pieces. This value of 2 is the average square, the average of the difference of distances, okay? Or the average distance, squared distance between points. Now, here is this remarkable fact, and I'll show you why this is so in a minute, but it turns out that for any distance matrix, n by n points, where n is greater than the dimension that those points reside in plus 2, then you can write the distance matrix completely in terms of C. There's a sort of nonlinear inverse formula where this lambda sub 2 of C is the second largest eigenvalue of the C matrix. And so if the number of points is larger than the embedding dimension plus 2, then D is uniquely determined by this nonlinear function of the center distance matrix. So you can recover that missing centering. So here's how it works in this example. There's C. That's the second eigenvalue, 2. That is the thing we were trying to recover, and then we just have this recovery formula. So even though this differencing operation is wiping something out, it turns out because these are special matrices, they're distance matrices, this missing component is lurking around as long as you have enough points. Now let me kind of just quickly explain why this happens. So here again is the decomposition of the distance matrix. I can write the distance matrix in terms of the Gram matrix K, and we can also have an analogous orthogonal decomposition of the Gram matrix in terms of this H and V. V is sort of the part, well, let me just say it this way. H is the part that you can recover directly from the differences of distances. That's sort of what you're able to measure. V is the part that you're blind to. And it turns out we can also figure out what this weight is. It's also an eigenvalue. It's an eigenvalue of this H matrix. So here's how it goes. It's pretty simple. And it's easier to see in terms of the Gram matrix than the distance matrix. That's why I've switched over to the Gram matrix. So there's that Gram matrix decomposition. We assume that our latent embedding is centered so that the mean of the columns is 0. So it's just centered around the origin. That means that Z times the all ones vector is 0. And if that's so, then lambda, this weight that we have to put on this missing component V, is an eigenvalue of H with multiplicity n minus the rank of Z, the embedding dimension, minus 1. So why is that? So that's what this is telling us then, that we have this eigenrelationship. We can recover it. And as long as n is greater than 2 times D, we can unambiguously identify this eigenvalue. And here's just the proof. It's very simple. You have your Gram matrix. Things are d-dimensional, so its rank is d. The Gram matrix is orthogonal, or the all ones vector is orthogonal to the Gram matrix. So that means that the dimension of the space perpendicular to all ones intersected with the kernel of the Gram matrix has dimension. This dimension is n minus d. That's this minus 1. That's that. Okay, so that's the dimension of that set of vectors. And if we pick one of the vectors in that set, then the Gram matrix times such a vector is equal to h times u lambda v times u. But because u is picked to be perpendicular to the all ones vector, and if you remember the definition of v up there, that part just gets wiped out, or this part just becomes u itself again. And so you have hu plus lambda u equals 0, and so it shows that lambda is an eigenvalue of the H matrix. Okay. So I don't know if that's comprehensible based on that quick thing, but I just want to impress upon you it's really not that complicated. It's a kind of a one-line proof once you see it the right way. So what does it mean? It means that we can, if we collect enough of these differences of distances or these comparative judgments, that we can actually recover the ordinal embedding uniquely up to rigid transformations. And so if we have a set of triplet comparisons selected uniformly at random, and we assume that the responses, these binary responses, follow like a logistic with parameter k star, the true Gram matrix for our latent embedding, and if we also, just for convenience, scale the embedding, or scale rather the Gram matrix so that the average squared entry in that matrix is independent of dimensions. We just don't want the size of the matrix to depend in some strange way on dimension. It turns out if you do all that, then the trace of the Gram matrix is on the order of n, the number of points, times the square root of d, where d is the dimension of the latent embedding. And then if you just solve, minimize the logistic loss over that constraint set, the set of PSD matrices that satisfy that trace constraint, then with high probability you can recover your k hat, the solution to that minimization will recover the true embedding with this accuracy. And so basically what it's telling us is that the number of judgments we need to collect from people is roughly proportional to the embedding dimension times the number of points, which is more or less what you'd expect because I have n points in d dimensions. There are n times d degrees of freedom. Okay, I'll explain where this comes from when I get into a little bit more of the details, but this was basically answering Tim's question. How many questions do I need to ask my pool of subjects in order to learn such a representation? Well, it depends on what dimension he thinks he'd like to work with. If he thinks people's perceptions can be represented in 2 or 3 dimensions, then d is 2 or 3, and n is the number of face images he's showing them. Okay? So that's sort of the high-level story. What I'm going to do now is kind of go in a little bit more to the details of how we get at these results, and I'm going to look at the general metric learning problem. And again, that's the case where I have this sort of auxiliary first raw high-dimensional representation of the points, and I'm going to take the ordinal information and try to find a lower dimensional metric representation that agrees with the ordinal information. And again, the special case of non-metric multidimensional scaling is just where the original points are in that kind of that trivial canonical representation. Okay, so we're going to collect a set of distance comparisons. They're selected uniformly at random, and the binary responses we'll assume are independent and probably correct. And so that just means this right here. So there's my distance metric, the distance between points, dk star. So k star is my kernel of that metric. Xi and xj are the 2 original point representations. And if that inequality between the distances is true, then it's going to be probably true that the response yt, it should be yt equals 1. The probability that yt equals 1 given those points is greater than 1/2. So that's how the responses are probably correct or probably indicative of these distance comparisons. Okay. And here's our measurement operator again. I'm just going to use this notation, the subscript t, to denote a triple like ijk, just so I don't have to keep writing ijk everywhere. So for a particular triple, we have the kind of measurement operator is this trace of this MT matrix times a kernel matrix, and this is the MT matrix. It would have this form then in the general metric learning case, where you just see all these various outer products between the different points. And ideally what we do is minimize something like 0-1 loss. So this would be 0-1 loss if you have a hypothetical, or if you say, okay, I think K is the right kernel for this metric, then it either agrees with the comparisons or it disagrees with the comparative judgments, the YTs you're collecting. So that would be 0-1 loss there. But we're going to use something like logistic loss or hinge loss, a convex loss function that's easy to optimize. And once we've picked our loss, and just for this talk, think about logistic loss, we'll focus on that, then I can define an empirical risk and the actual risk, the expectation of that. So this is the set of all the triplets I've collected, and I'm just averaging up those logistic losses. I'm saying how well is K predicting the responses I've collected from people, that's the empirical risk, and then the expectation of that is the actual risk function. So that's the original set of points. We're going to try to find a new metric that agrees with the ordinal information we're collecting. Here are the three things we're going to do. First of all, we'll try to find a risk bound. So how, if I solve an optimization, minimize the logistic loss over a set K of kernel matrices, our K hat is my solution. So how good is that in terms of risk relative to K star, the presumed generative model? And it turns out that we can relate it to something like this. So we'll have a bound of this form. I'll say more about that as we go. There's also an analogous minimax lower bound, which is essentially about the same up to logarithmic factors. So this is showing that we really can improve on the procedures that I'll tell you about. And then finally, I'll sort of show how you can go from these risk type bounds to an actual recovery bound on the metric. Because again, especially in these psychometric applications, they don't really care about predicting people's judgments. They really want to then inspect that learned metric and understand what was driving people's judgments. So they want to know, what is this K star? And so that's the last thing I'll talk about. Okay, so let's first of all talk about the risk bound. So the set that we're going to kind of constrain things to lie in is the set of positive definite matrices. So P here, I should say, is the original high dimensional representation. So it's a p-dimensional representation. K then is a positive semi-definite matrix. P by P will constrain the trace of that matrix to be less than some value lambda. That's sort of encouraging a low dimensional metric. And then we'll also just put another constraint to make sure that things are bounded. Basically, that's all that last constraint. The max of the inner products is bounded. So things are not unbounded. Okay. And then I'll let K with a superscript asterisk just to note the metric that actually minimizes the risk, and K hat will be the kernel that minimizes the empirical risk. And what we can show then is that if we have any Lipschitz loss and we take any delta greater than 0 that we like, then with probability at least 1 minus delta, we have a risk bound that looks like this. So it has two terms, and maybe as we go into it, I'll discuss the two terms a little bit more. But basically, the two terms are coming from a kind of fairly standard strategy where we're using McDermott's inequality and a Rademacher complexity bound. And sort of the interesting part here in terms of novelty is just working out what this Rademacher complexity is. So let me explain what the Rademacher complexity is. So here is just a kind of way to write out what's the relationship between the true risk and the empirical risk for a given kernel K. I can just always write it like this. So the true risk is less than or equal to the empirical risk plus the expectation of the soup of this quantity, which is the maximum deviation of empirical risk from true risk. And so what we really need to do is get control or figure out how big this soup difference of the empirical risk and true risk could be. Here we're just doing a couple of simple inequalities, matrix inequalities, and we end up with this inequality right here, and this guy is the Rademacher complexity that we need to compute, the Rademacher complexity of our measurement model. And in order to get a handle on that, what we need to do is really figure out what are the spectral characteristics of this operator. So this is the operator norm of the squared measurement matrices averaged over all possible measurement matrices. So all the possible triplets we could collect. We're just kind of looking at what are the spectral characteristics of this measurement operator. And it turns out that if you look at that carefully, you can bound it by a constant times the spectral norm of x transpose. So x is again the matrix of the original point representations, and so this is the sort of the spectral norm of that quantity over n, where n is the number of points. And so then with that we can use the matrix Bernstein inequality and get this bound on the Rademacher complexity. So I'm not going to go into more details of that, but the point is the really kind of part that's special for this problem is working out this kind of spectrum. Okay, so let me illustrate what this theorem is telling us in the case of an isotropic x. So here I'm just going to take the points x, the original representation, to be in Rp and Gaussian distributed with zero mean and scaled so that their expected norm squareds are equal to 1. And we'll assume that we have slightly more, at least slightly more points than we have dimensions in that original representation. We have to learn a p by p matrix. We're going to need a little bit more than p points in order to do that. So under that construction, then with large probability, the spectral norm of this XX transpose is like n over p. We're going to generate then a low dimensional metric sort of uniformly at random. So this is taking u uniformly at random from the Grassmannian manifold. So this kind of gives us a low dimensional subspace in a random generic orientation. And then UU transpose is my kernel matrix. And I'm just scaling that by p over the square root of d. And again, that scaling is just so that the average entry, the size of the average entry in this K star is dimensionless. We don't want to have it depending on dimension in some funny way. And if we do that, then the trace of the kernel matrix is p times the square root of d. That would be the lambda in our theorem before. And if I plug that all in, then you get this excess risk bound. And the key thing here is just that this d times p is, again, the degrees of freedom in a d-dimensional metric on Rp. So it sort of agrees with your intuition. Okay? All right. So now let's talk about this idea of actually not just what that risk bound is telling us is that we can learn a metric k hat that predicts people's responses nearly as well as the true underlying metric. But can we actually say something about how close that k hat is to k star? That's the recovery problem. And for this, in the last part, we didn't really need to know what the true link function was between the metric and the people's responses. Here we have to assume that link function is known, and we're going to use log likelihood loss. So again, if we assume that the responses follow a logistic model, and it should just be logistic regression. And if XX transpose is well conditioned, and both k hat and, I'm sorry, that should not be a hat there. If both k star and k hat are low ranked, then with large probability, we'll actually be able to say that k hat is close to k star in terms of Frobenius norm. And it has almost the same form as the previous risk bound. So how is that happening? Well, under this maximum likelihood setup, the difference between the risk of k hat and k star can actually be expressed in terms of the KL divergence between those two distributions, the one with k star and the one with k hat. And again, the script t is just denoting all possible triples. So that's essentially the expectation. I'm just averaging over all the triples we could collect. There are roughly n cubed of them. So then, going from the KL divergence, we can actually bound that in terms of the square differences between these inner products, where this constant c sub f is the infimum of the derivative of the length function f. And so basically what's happening here is we're thinking about the logistic loss. We're assuming our measurements are bounded. That was one of our other constraints. So we're sort of operating in the, think of it as operating in the more or less linear region of the logistic. We're not out there in the saturated part, so we can invert that logistic function. That's sort of what we're saying there. Now, the spectrum of the measurement operator, here's kind of an important point. It turns out that it's almost perfectly uniform. It's not quite uniform, but it's almost perfectly uniform over its range. And so what that means is that it's a nice stable inverse for the part that we can get at. And again, that's this H component. That's the part that's observable. There is a null space in this operator because it's differencing. H is the part that's not in the null space, so we can get that guy back, and we can get him back stably because this measurement operator has a nice spectrum on that range. And then, for the same reason I showed you before, it turns out that the component that we can't observe directly can be inferred directly by looking at this eigenvalue of the matrix H. So we can get that piece back too, also stably. So putting that in then, what it means is we can drop down from that square difference of inner products to this Frobenius norm that I'm showing you here. And then the last ingredient is just to pull out the x component here. And we can do that by just taking the minimum eigenvalue or singular value squared of this XX transpose matrix. And so that's basically where, so what I have to have is, obviously, X itself has to span the entire RP space. If that's not happening, then X itself is making me blind to certain directions. And so this is just saying that the smallest eigenvalue of that matrix is also bounded away from 0. And if that happens, then things are nice. So again, if X transpose is well conditioned, this is what would happen if, again, I were taking Gaussian random vectors as my initial points, for example, then this minimum singular value times n, the number of points, divided by the total number of triplets. If you work out what that is, that's basically 1 over p squared, where p is the dimension of that original representation. And we have this risk bound before, so I can plug that into the left-hand side up there, and that's what would give me then what I had before. Maybe I'll just bounce up to it. Where is it? Oops. That's where, if I just kind of pull all that together, I get this result. So for recovery, the kind of added thing that's important is that the x vectors, the original representation, span all of RP nicely. And then if that's happening, then actually you can recover k hat close to the original k star. Yeah?
I think I missed something small. So script T is a set of all possible triplets?
Yeah.
Script S is the actual set of triplets?
Yes.
Here?
Yeah.
Okay.
Yeah, so here, this is an expectation, right, over the responses. So I'm just averaging over all possible questions that we could have asked to compute that expectation. But yeah, we're only observing a subset of them. The question is, how many do we have to observe in order to recover the matrix. And it's basically the same story as before. If we were, again, having our original points being more or less isotropic like this, and if we have enough of them, then it's going to be about d times p total measurements we have to collect. Even though there could be far more possible questions we could have asked people, we only need that many. So let me kind of bounce back through this stuff. And right, so now I only have a couple more slides here. I'm going to talk about sparse metrics. And this is interesting because with Martina, if you remember, she was looking at these chemistry problems. And what she and her students did is they took the chemistry molecules, these visual representations, and they just create a laundry list of all the visual features that students might be assessing in their judgments. So some of those features were like counts of various atoms, lengths and angles of bonds, and so on and so forth. So they had a list of about 100 visual features or percepts that they think might be involved with the students' judgments and comparisons. And then what they wanted to know is, in that long list of 100, what are, say, the 5 or 10 that really seem to be most important. So they wanted to select a subset of the dimensions that drive the perceptions of students. And the idea is that maybe beginning students are missing certain key features that experts do attend to. So they would compare beginning students with more well-trained experts and try to see which features are beginners missing, and then that would inform how she designs better tutoring systems. That's the whole story there. So sparse metrics, what would that mean? Well, we were talking about low-rank metrics. It just is some k-matrix that looks like this. Its structure is simply this, just low rank, but we might also, for Martina, be interested in recovering sparse and low-rank kernel matrices like this one. Okay? And so to do that, one thing you could try is you could say, well, let's just modify our constraint set. Instead of looking at the trace, let's look at the 1-2 norm. So this is basically like a group lasso norm. It's saying just select certain rows or columns. Try to find a metric where most of the rows or columns are equal to 0, like I'm showing here. So that's just a group lasso type of penalty. So we can work with this set. It's, as you would expect, this 1-2 norm is greater than the trace norm. And so this new constraint set is a smaller set. It's a subset of all low-rank matrices. A subset is sparse and low-rank matrices. Makes sense. So we're going to try to add an additional constraint, if you will. We want it to be sparse and low-rank. So the question we had is, how much would this help? Could we do a lot better? And again, we're just going to solve our empirical risk minimization, just logistic regression, for example. And one of the things we did then is we derived this minimax lower bound. So here in this minimax lower bound, we're working with this kind of group lasso constraint set. So it's a stronger constraint. So this lower bound is a lower bound for the original problem where we worked with the trace norm as well. And what it's saying is that the excess risk is bounded below by this quantity that you see there. And the important thing is just to compare it back with our upper bound that we had earlier. And it essentially looks the same apart from basically log factors. This log p shows up here but isn't showing up there. So this lower bound is essentially matching. And so what it's telling us is that in general, sparse metric learning is essentially as hard as general low-dimensional metric learning. The important thing, though, here is that this is just saying there exists some x, not that it's true for every x. And so, in fact, in this minimax lower bound construction, we're just taking x to be the identity matrix. And so that's a matrix whose columns are very coherent with the canonical basis. If we instead had columns that were maybe very incoherent, we might be able to see a difference between sparse metric learning and just general low-rank metric learning. But that's something we haven't really explored yet, but I think something like that could be true. So I'm just going to wrap up with some numerical experiments to show you how this all shakes out. And we're going to essentially use the same construction that I had before, where we take these isotropic Gaussian points as our original representation. We're going to take a random subspace to generate our low-dimensional representation. And this was the risk bound that we're expecting to see in that kind of situation. So here I'm plotting the relative excess risk. So this is the excess risk normalized by the risk of the of k star, the optimal. And I'm comparing the trace norm constrained optimization, the L12, the group lasso constrained, and then one that just has no constraints, just find a PSD matrix that agrees with the triplet measurements. And so you can see that in both cases, adding the constraints helps, right? It's doing something, that's what we expect. And we also see that in the case where things are sparse, the group lasso is doing a bit better than the trace norm. And in the case where it's not sparse, the trace norm is doing a bit better than the group lasso. Again, that's what we would expect here. But we haven't seen a large difference between the trace norm and the group lasso in practice, either in simulation or in our real data experiments. And so it's not clear whether it's really worth the bother of trying to do that or not, but it's something to keep in mind. And here are some other experiments just to kind of see that this kind of scaling that we think should be there actually shows up. I don't know why it wouldn't, since the math is what it is, but here is what we're looking at is the relative excess risk, and we're saying how many samples do we need to get that to be less than 10%, okay, just as a kind of stopping point. So how many measurements do we need so that the excess risk isn't too much larger than, or is small relative to the risk of k star. And here what we're doing is we're number of measurements versus the dimension that we're embedding in for some fixed original dimension. I think the original dimension was 100. So the original dimension is 100, and we're embedding into 2, 4, 6, 8, 10 dimensions according to that, whatever that k star was. And you see as the embedding dimension goes up, the number of samples we need to achieve this relative excess risk is going up linearly. That's what we'd expect. That's the D up there. So it should, the sample size should need to grow linearly with D. And here we're fixing the embedding dimension and then varying the extrinsic, the original dimension P, and we also see the linear growth, which is what we'd expect. So everything seems to agree nicely with the theory. And I'll stop there. I just want to mention this is joint work with former students, Lalit Jain and Kevin Jameson, and one of my current students, Blake Mason. This paper, the first one, is sort of the one that summarizes most of what I've just discussed. That was in NIPS this year. This previous paper from NIPS the year before that was specialized to just the ordinal embedding case. And then this is a paper with Martina where we actually applied some of this for this chemistry learning problem. So if you're interested more, you can look at those. And I'll stop there and take any questions. Thank you.
So the talk is open for questions. Axel?
Krishak, very nice talk.
Thank you.
Thanks a lot. It was really great. So I wonder, is there a connection to, in a sense, compressive sensing from the perspective of the Safiya-Lippenstrauss embedding theorem? So what I mean is, there you ask, in a sense, a kind of converse question, right? You have a bunch of high-dimensional vectors, and you want to compress them down to a low-dimensional space. Essentially, you get locked dimension. Up to, let's say, delta, and then you pertain all the metrics up to a small perturbation.
Yeah.
So do you see that? Because there you also get you get this p log p. There you get the delta log 1 over delta. I think so. It looks somehow similar, but it's a converse question in a sense.
Yeah, that's an interesting point. I hadn't really thought about it, but you're saying, if I have a high dimensional representation, I have a bunch of these ordinal constraints. If there are only n points, though, maybe I can embed into a lower dimensional space, a la Johnson-Lindenstrauss, and how does this relate to that question? Like, I should be able to preserve,
the embedding
yeah,
such that
that
all the
preserves,
metrics,
yeah.
all the pairwise distances are pertained.
yeah,
But of course, you cannot pertain it exactly, but you do it up to
Yeah.
a small perturbation,
Yeah.
let's say called delta.
right. Yeah, I'd have to think about that. That's an interesting question I haven't actually thought about. Here, I guess our goal, at least in terms of the objective, is to try to
I fully
not
understand.
flip as
Somehow
many of
it's
those.
very
yeah.
Somehow it's different, but
Yeah.
somehow it feels a little that
Yeah.
there might be an analogy, but I don't understand it at the
Yeah,
moment.
that's a good question. I'll ponder that. Maybe we could chat about it more after I get a little
And then I
time to
have a
think about it.
second question, if
Yeah.
I may. The second one is, could you imagine, okay, this is probably a weird question because I never worked in neuroscience, but could you imagine that somehow one could design an experiment such that you somehow maybe can try to learn, let's say, the internal representation, the dimension of the internal representation of a human being?
That's
What I mean,
yeah.
is you could assume mathematical, let's
Yeah.
say we want to go to
Yeah.
dimension 2 or 3
Right.
and then figure out
Yeah.
which maybe works best, right, with you,
Yeah.
if you have your question catalog, but you could try to think about, I could try to learn actually how we, in which dimension essentially we present.
Yeah,
our features.
so the psychologists that I work with do this in two ways. One, which is a natural one, they would just try to find embeddings in 2, 3, 4, 5, etc. dimensions, and then see, if
Which
they
fits.
look at which
And
fits
do
better.
you know by curiosity what they
Uh,
what kind of answers they
Yeah, so for that's really one of the questions that motivated the faces, the motion faces that I showed you before. There's classical work in psychometrics that says there are 3 salient dimensions to the perception of emotion in faces. It's positive, negative, some measure of intensity, like you could be kind of angry or super angry, happy or euphoric and joyful. So there's some measure of intensity of emotion, positive, negative emotion, and then another dimension they think is called surprisal or something, I guess. So there's some conjecture that there are 3 salient dimensions. So one question is, if you run these experiments and then try to learn these embeddings, can we see evidence for at least 3 dimensions, or is there a 4th or whatever? This is the kind of question they wanted to ask. And I thought that's great, but I mean, if we don't even know if we can recover a metric from a assumed generative model, then what are we doing, right? So that's what motivated this work. So that's exactly what they do. So they either try out different dimensions and then see how good the fit is, or they might hold out some of these triplet comparisons and then try to adjust lambda, which is the, say, trace norm constraint, which essentially controls the ultimate embedding dimension, adjust that through some cross-validation and then say, oh yeah, cross-validation told us that it's 3 or 4 dimensional.
So I can imagine when comparing the faces, for example,
Yep.
there'll be some examples where the person's absolutely clear that this one's closer than that, and other ones where it's, they can't make a decision. It's
Right.
not at all clear.
Yes.
So can it all be adapted with some sort of weighting on how confident the comparisons are?
Yeah, that is a tempting thing to do, and we have, in similar experiments, allowed people, instead of having a left-right kind of option, giving them a slider, right? So they could put it in the middle if it looks like the same, or move it way over to one of the extremes, with the idea that maybe we can get a few more bits of information rather than just one from each judgment. And we didn't have a lot of success with that. I mean, we thought about it kind of carefully and actually built a system to collect data like that. One reason that might be is there are some other data from the psychometrics literature that really suggests that people can't really provide information much more than just a few bits anyway. So even if you give them the slider, they really tend to not be able to make very fine-grained judgments to give you much more than a bit of information. But yeah, we've thought about that a little bit, and but we haven't found enough empirical support to pursue it further.
One more question.
Yeah.
For the trade talk first, I was wondering if, this is really related to experiments, if there's any way to do this in a sort of, active way a little bit.
Yeah, so that's another thing that was one of our original motivations, because you don't want to necessarily ask really easy questions. And if you're doing the faces, for example, immediately the metric that you're sort of learning as you go is figuring out positive and negative emotion, right? That just kind of sticks out. There's a very strong signal there. So very quickly you can learn to predict, if you will, whether it's a positive or negative emotion being displayed. And so you might say we don't need to keep asking people those questions because it's sort of already figured out that dimension. So we looked a lot at adaptive, active methods that would sort of select good queries to put to people rather than randomly choosing them. And to be honest, I think it's very difficult. And so I backed off of that, and I went back to an even easier problem, which is just ranking. So, which is kind of like just embedding into one dimension. So now suppose I'm just giving comparative judgments. Which one looks happier, right? I give you two faces, which one looks happier? And then I have a bunch of faces, I'd like to rank them from most happy to least happy. How would I do that adaptively? Now, if there was no noise in the process, I would just do quicksort, right? Because I'm just doing comparisons, then that would be the optimal adaptive algorithm. And so there's a large literature on noise-tolerant quicksort or noise-tolerant sorting algorithms that do try to do things adaptively. And my general opinion and experiences is that these judgments are just so noisy. There are going to be so many that are almost like coin tosses that any kind of approaches that are based on kind of noise-tolerant sorting algorithms don't work in practice any better than just random methods, random designs. And so we've kind of backed off of that program of trying to figure out how to adaptively choose these questions to ask people, at least in this context. I think adaptively chosen questions would be more appropriate if your goal is some sort of clustering rather than some sort of embedding. And I can tell you more about what we're doing with kind of clustered rankings in adaptive selected kind of questions where we do have some promising and encouraging results. So that's a good question, but yeah.
I think even in an offline setting, right, I mean, you have all these conditions that depend on the matrix X. Even without seeing any results before, this could be also a good question.
Yeah.
No more questions? Okay. So let's
Okay.
thank Robert again.
Thank you.